In this tutorial, we will evaluate the structural integrity of a solar carport structure, which is a steel-framed canopy, designed to provide vehicle shelter while integrating solar panels on the roof. This solar carport structure consists of columns, bracings, rafters, and purlins, designed to support solar panels while providing vehicle shelter. Now, to create the carport structure in IMDAS, we create a 2D line model which shows the front view of the structure and save it as DXF, then we will import this DXF file in IMDAS. Now, using the DXF import command, we import the structure. We will select beams using Select tool and create groups for column, rafter, and then bracings. By creating groups, it will be easy to modify cross-sections for all members within that group. Now we will create custom pipe sections to use for column, rafter, and bracings. Before we define section properties, we will change the units to millimeter. We will use standard rectangular hollow section for purlin. IMDAS has a library of standard cross-sectional profiles defined for hot-rolled and cold-rolled steel members. Now, we will assign cross-sections to all members in the group. Using the Properties panel, it is simple to change the cross-section or any other property of the members. Now, using Pattern Group command, we will create patterns of the member groups, which we created earlier. Now, we will create a single purlin member. To do this, we display the nodes and select the two nodes to create the beam. Then we also adjust the beta angle of the section. And then we pattern the purlins to complete the frame. Our structure is now complete. To simulate real-world conditions, we need to consider multiple loads on the structure. The self-weight is automatically calculated based on material density and gravitational acceleration. The GI sheet weight is applied uniformly along the roof slope with a load of 2.2 Newton per meter. Panel weight is distributed along the roof frame, with a load of 88.5 Newton per meter. Additionally, wind loads are applied as per IS 875 standard, to ensure accurate structural behavior under environmental forces. Now, let's define the support conditions. In the support command, we select all the nodes on the ground and we specify fixed condition for these nodes. We can visualize the supports in the graphics window from the display options. Now, using self-weight command, we apply dead loads to account for the self-weight of steel members. Now, we select all purlin groups to define the GI sheet load, and then in the UDL command, we specify the load in global coordinate system. Now, we select the purlin groups which are supporting the solar panels, and then in the UDL command, we specify the weight of the panels as distributed loads. Now, we select the purlin groups to define the windward loads, and then, in the UDL command, we specify the loads in local coordinate system of the members. Then, we define the leeward side wind loads. After all loads are defined, we need to mesh the structure using the mesh command. We can control number of elements in the members for more accurate solution. The structural mesh consists of nodes and elements, forming a discretized representation of the structure for analysis. Now, we set up structural analysis. We need to define load cases for our analysis, using the load case command. Now, for design check, we will define load combinations, as per IS 800-2007 limit state method. All the relevant load combinations are added to the analysis using the Add button. With all load cases and combinations defined, let's run this static structural analysis. IMDAS performs finite element analysis to compute member forces, deflections, and support reactions. After analysis is complete, we will visualize the deformed shape, check shear diagram and moment contours, and examine reaction forces at supports. IMDAS has post-processing tools, enabling the visualization of bending moment and bending stress distribution contours. Now, we check if our steel members meet design code requirements. If any members are overstressed, we can optimize the design by increasing the section size or adjusting the bracing configuration. Using the member design command, we can select the design code to check the utilization of the members. The summary sheet highlights the utilization ratio and design status of the member. Here, we can see that all members are passing the design code check criterias. We can also plot the utilization ratios to visualize the member design. We can easily review detailed code check calculations for any member by simply selecting it from the list. In the Detail Calculation tab, the software generates a comprehensive report, including bending moments, deflection limits, and stress ratios, helping ensure that every member meets design code requirements. That concludes our tutorial on designing and analyzing a steel carport structure using IMDAS. Thank you for watching. We hope you found it informative and helpful.